In this example, we're given the following polynomial, p of x is equal to 3x to the fourth plus x to the third minus 17x squared minus 5x plus 10. And given this, we're asked to solve the equation p of x equals 0, and we're told to use the rational roots theorem to help us do so. And I'll abbreviate that as RRT. So recall that the rational roots theorem says that if you take all the factors of p, where p is your last number, and put them over all the factors of q, where q is your leading coefficient, in that list of numbers, you're going to have your rational roots, or your rational numbers that cause this polynomial to equal 0, which is the equation we're trying to solve, p of x equals 0. So first things first, all the factors of q are 1 and 3, and all the factors of p are 1, 2, 5, and 10. So if I make my list of p over q's, I'm going to write it this way, plus or minus, and then my whole list. We're going to have 1 over 1, which is 1, 1 over 3, which is a third. So I'm just taking all these factors of p one by one and putting them over every single factor of q. So now I'm on 2, so 2 over 1 is 2. Then we have 2 over 3. And then 5 over 1 is 5, and then we have 5 over 3. And then 10 over 1 is 10, and we've got 10 over 3. And so that's my list. Now, unless you're really unlucky and you just happen to not find it, you don't have to go through every single number here. You just need to go until you find a 0. Once you find one, you're going to be able to reduce your polynomial down with synthetic division, and then your list will get smaller, and you can keep doing this. So first things first, I'm going to try positive 1. I'm just going through the list in order. Now, you have two ways to test this. You can either plug in the value to the polynomial and see if it equals 0, or you can just start doing synthetic division right off the bat, and then if you get a remainder of 0, you know it works. So just to show that what we're doing is finding zeros, I'm going to start by plugging into the polynomial, and I'll do synthetic division once I find one. So if I do p of positive 1, 1's easy to plug in, so 3 times 1 to the fourth. Really, all these variables, x to a power, 1 to any power is just 1. So this whole thing is just going to be 3 plus 1 minus 17 minus 5 plus 10. And if I add this up, I get 4. 17 and 5 is 22. And then plus 10. And then I've got 14, 4 plus 10, minus 22. And that's definitely not 0. So at this point, I don't even care what the value is. It's not 0. So positive 1, that doesn't work. Well, let me try negative 1. So p of negative 1. Now I just need to be a little careful. Anything with an odd power on the x, it's going to flip, because a negative to an odd power is still negative, where a negative to an even power is positive. So I'm going to have 3 minus 1 minus 17, the sign doesn't change, plus 5, because I have negative 5 times negative 1, and then plus 10. And if I work this out, 3 minus 1 is 2. Negative 17 plus 5 is negative 12 plus 10. And 2 minus 12, that's negative 10 plus 10, which is definitely 0. So I found one of my rational real roots. Negative 1 works. So what I'm going to do is I'm going to do synthetic division to reduce my polynomial down using this root. So I'm going to have negative 1, because that's my root or my 0. Then I just pop off the coefficients here. So 3, 1, negative 17, negative 5, and 10. Bring down my first number, which is 3. 3 times negative 1 is negative 3. Add these up, I get negative 2. Negative 2 times negative 1 is positive 2. Negative 17 plus 2 is negative 15. Negative 15 times negative 1 is positive 15. Add that to 5, I get 10. And then 10 times negative 1 is negative 10. 10 plus negative 10, that's a 0. So again, if you picked a 0 correctly, when you do synthetic division, your remainder should be 0. And then what happens is that whatever the highest degree of your polynomial was, it's just going to drop down by 1. So this becomes 3x cubed minus 2x squared minus 15x plus 10. That's my new polynomial. And I use -1 to get here. So now at this point, what I would do is I would use this right here and find the next 0. So my new list here, my new p is, well, actually it doesn't change. My p is still 10. My q is still 3. So I'm still using the same list, but notice I know it's not +1, and I know it's not -1 because I've already done those. And so that's pretty straightforward. Now, what you would want to do is go through this list and try every single one until it works. Of course, I'm going to sneak a little bit since I know that I want to use 2/3 because I designed this question after all. So I'm going to pick this, but there is no way I'd know that I need to pick that. I would actually sit here and I'd try 1/3, I'd try 2, and then if I don't get frustrated and start jumping around, I'd get to 2/3 and I'd try that, and then it would work. So let's test it right quick. Since you've seen that when you plug in as a polynomial, you get 0, but when you do synthetic division, you also get 0, I'm going to start with the synthetic division. So I'll do 2/3, and then synthetically divide that into my new polynomial, which is 3, -2, -15, and 10. So bring down the 3. 3 times 2/3 is 2. 2 plus -2 is 0. 0 times this is 0. Add that up, I get -15. And then -15 times 2/3, well, 3 goes into 15 5 times. So that becomes 2 times -5, which is -10. Ta-da! And that's a remainder of 0. And so now my new polynomial is 3x squared plus 0x minus 15. And I could rewrite this guy as 3x squared minus 15. And so now, if I look at this, I can factor out a 3. And I've got x squared minus 5. And if you go through this list of numbers and try them, you'll notice that none of these make this equal 0. So we've got a 0 of -1, and we've got a 0 of 2/3. So we've got 2 zeros, but of course, look, we've got a power of 4. We're expecting 4 zeros, right? But if you go through this list, none of these are going to make x squared minus 5 equal 0. None of them work. Well, how is that? We're told that all the rational roots should be in this list. But there's the thing. This has roots, it has zeros, but they're not rational. They're irrational. You might recognize that this looks like a difference of squares. And so I would write it as 3 times x minus something and x plus something. Well, just as an example, a reminder of difference of squares, if you had x squared minus 9, that would turn into x minus 3 and x plus 3, which is really just square root of 9, right, in both places? Well, you'll get the same thing here. Square root of whatever that number is, where that number is 5. So this is square root of 5, positive and negative. So my other zeros, which are not in that list, is plus and minus the square root of 5. And I have to get that just by inspection. I look at that and I see that, oh, that's a difference of squares. My square roots are the square root of 5, which is an irrational number. So that's the one flaw with the rational roots theorem. I don't know if I'd even call it a flaw so much as just for learning this and working it out, it can be an inconvenience. If you didn't notice that your final polynomial here was x squared minus 5, and that the roots of this guy are irrational, just looking at that, you might spend all your time going through this whole list and seeing that none of them work. So make sure after every step when you're doing a problem like this, look at your new polynomial. And if it's like something that looks messy, like this cubic or whatever, go ahead and keep trying out zeros from this list. But if you get down to something like x squared minus a number, even if that's not a perfect square traditionally, like 9, which would be 3 and 3, or 16, which would be 4 and 4, if you've got x squared minus a number, think about that for a moment. You could do square root of 5 on both sides. It's just an irrational number. So that's a very common thing that people miss, and they spend a whole lot of time pulling their hair out. So be careful about that. Always look at your resulting polynomial. So in summary, solving the equation p of x equals 0 finding the things that when you plug it in here, you get 0. To get the rational answers, like -1 and 2/3, you use the rational roots theorem. To get the other ones, you've just got to be careful and look at what your result is as you go. So our zeros are -1, 2/3, square root of 5, and negative square root of 5. And that is an example of using the rational roots theorem as far as you can for a polynomial that has some irrational roots.